Okay, so this video is the first section in chapter 6, 6.1, section 6.1, which deals with radians. Now, up to this point in your math career, whenever you've measured an angle, it's always been measured in something we call degrees. And there's 360 degrees in a circle. But now we're going to talk about a different type of measure that you can use for angle measures. So like length, we could use inches, we could use feet, we could use centimeters, we could use meters. So there's lots of different units that you could use for length. And up to this point, angle measures, or rotation, amount of rotation, has always been measured in units called degrees. And so if you look at your calculators, now we're not going to use our calculators too much for this, but in your calculators, there's always some on your screen. Generally, there's some sort of readout that in this case, in this type of calculator, it says DEG, which means degrees. Some calculators have a D. Some calculators don't display it, so like this more fancy graphing calculator don't display it, but if you go to mode, it'll show you that we're in degrees rather than radians. And so if I wanted to change that, I would just come down and select that, and it would switch it from degrees to radians if we're trying to use radians. In this calculator, it says DEG, which stands for degrees, and if you want to change your radians, you hit this button here that says DRG. So hit that, and you see it right now is in degrees, and so you'd cursor over to radians and hit enter, and now if you look, it will say RAD, which means radians. Okay, gradians is the other one, and don't worry, we never use those. Okay, so radians. So early 1700s, people started using this idea of radians, and so instead of degrees, they related the amount of rotation. They related it to the radius, how much the radius was. So, for example, here I have a circle of radius r. And the arc, if we take that length and lay it down on the circle, so this arc length is r. You lay it down on that part of the circle, and then the angle that cuts out that arc length, the central angle, is by definition 1 radian. It's about 57 degrees. Okay, we don't use that as a conversion. We'll talk about conversion in a minute. So this doesn't matter how big or how small the circle is, because as the radius gets bigger, of course, the arc length, as a result, gets bigger as well. But the central angle, 1 radian, will be the same. Whether I make this circle small or big, 1 radian will be the same amount of rotation. Okay. There is a video, if you open up the PDF of these notes and click on this, I think it'll take you to a nice little demonstration of this sort of the definition of what a radian is. So I would suggest that you stop right now this video and switch over to your notes. Click on this and watch that little video. Or what you can do, I think I recorded a video talking through it as well. So there's another video in this post that you could use, that you could look at as well, or you can open up the PDF and kind of look at it as well. Okay, so let's look at some conversions from degrees to radians. There's set angles, set amount of rotation that we should just kind of get comfortable with and use. The first couple times it's going to be a little cumbersome. If you looked at that demo or my other video associated with these notes, you'll find that half of a rotation, or 180 degrees, in radians is something called pi radians. And then, so at this point, and then if we rotate all the way back around to where we started, 360 degrees, well, that's 2 pi. Okay? So if we think about 90 degrees, what portion of that circle are we talking about? We're talking about 1/4 of it, or 1/2 of 180. So this, in terms of radians, is pi over 2 radians. Now, radians are an interesting sort of dimension. It doesn't have any like units. I know that seems like it's a rotation. So if degrees have a degree, how is a rotation measured in radians dimensionless? And so it's a little confusing, but it's like we are doing it in we're giving you the unit in terms of r, but it's not. It's like r divided by r. So like it's dimensional. So sometimes we will write pi over 2 radians. Sometimes we'll just say pi over 2. Now, if I mean it to be degrees, I must use the degree symbol. So 57.3 with a degree symbol, I know this is 57.3 degrees. If there were no degree symbol, then that would be by default radians. And then we would say, oh, so there's no radians, like I could write radians, so pi over 2 radians, or I can just leave it off. And so there's no degree symbol, so I know by default it is radians. So radians, sometimes we'll write in the units radians, but technically they are dimensionless. And it's kind of important because we're going to take derivatives later, not in this class, but in later classes you'll take derivatives. And so you kind of have to have everything in radians. Now, to start with, this is going to be confusing, and you're going to be like, what? Why are we doing this? This seems so bizarre. Like, it seems so cumbersome. But eventually you'll start thinking of these measures in radians, not in degrees and then radians, because you'll use them so much, especially next year in Trig Calc. All right, so what is this unit? Actually, just pause the video and then write all of these angle measures in radians. Okay, this one is 3 pi over 2 radians, 270 degrees. This one is negative, so just like degrees can have negative, radians can as well. This is negative pi. This one's 1 full revolution, so that's 2 pi, positive 2 pi. This one's in negative direction, so it's the magnitude is the same as 3 pi over 2, but it's negative 3 pi over 2. And then this one's a little trickier. Think about 45. What fraction of, so like this is the reference angle is 45. So think about it. We have 1, 2, 3, 4. We have 5 45s. Think about what 145 would be, right? It's 1/4 of 180. So this will be pi over 4 up to here. Just that will be pi over 4, 45 degrees. So this is 5 of those. So this is 5 pi over 4. All right, and then, I'm sorry, we're supposed to be doing these in degrees and then in radians. Well, all right, well, we've kind of already talked about what they were. This one would be 225 degrees. This one's negative 270. This one is 360 degrees. Notice I'm putting degree symbols on all these because without that, by default, it would be radians, and we don't mean it to be 180 radians. It's 180 degrees. 270 degrees, and this one 90, of course, 90 degrees. Okay. We should kind of already know that from last chapter, but not bad to practice those as well. All right, and then this last one, it's almost 1 full revolution, 30 degrees shy of that. So that's clearly going to be what, 330 degrees. And then what will that be in radians? Okay, so think about this. 30 degrees is the reference angle. 30 degrees, if it was up here, 30 degrees, what is that in radians? So think about what fraction of 180 that is. That's 1/6. So this would be pi over 6. 30 degrees is pi over 6. So this is 11 of those, right? So 12 pi over 6 would be 2 pi. We're shy of one of those. So this is 11 pi over 6. Okay. Now, sometimes we'll actually do a conversion using like dimensional analysis. Here, these are certain ones that we should just kind of know based on angles, and we'll practice some more of those in this XY coordinate plane here with the circle. We'll practice more of them here. But some we will just know based on the reference angle. 45, okay, it's got to be some pi over 4. Reference angle of 30, okay, it's going to be some pi over 6, that kind of thing. So we'll know those with a lot more practice. But sometimes we'll use sort of dimensional analysis. And yes, 2 pi is equal to 360, but it's easier to think of pi equaling 180, just smaller numbers. So 45, I mean, if we had to, we would say, okay, 45, that is 180 degrees over pi, and then we would simply use dimensional analysis and reduce that, right? 45 goes into 180 4 times, but we should really just memorize the fact that 45 degrees is pi over 4, 1/4 of a half a circle. All right, negative 225. Well, this, remember, was positive 225, but now negative 225 would mean going this way, and so that's just going to be negative 5 pi over 4. And again, if you needed to do dimensional analysis, you certainly can. All right, now this one's not one of our common angles, so yes, we do need to multiply this, and so do I multiply? Let's talk about this. How did I decide to do pi over 180 degrees? I need my degrees up here to cancel with my degrees down here. So I know my 180 degrees is in the basement, in the denominator here. And then pi, again, radians if I wanted to write it. But I know that pi stands for radians because I didn't put a symbol. Remember, technically, radians are dimensionless. Okay, so what we want to do is we want to cancel, reduce the 404 and the 180 degrees. And I think that ends up being, we can divide both by 4, and that gives us 101 pi over 45. Yeah, over 45. Okay, so that's a wacky sort of conversion. It's not one of our common angles. These are what we refer to as our common angles. 404 degrees is kind of a wacky one. So 101 pi over 45. All right, so now this one's a little trickier. If we wanted to, we could sort of convert it to a decimal. That might be a little bit nicer because 12 minutes, that's kind of nice. We divide that by 60, and that's simply a 0.2, right? It's this would reduce to 65.2 degrees. Okay. All right, and then we can convert that, again, pi over 180 degrees. In this case, we might want to get rid of this decimal by multiplying top and bottom. Usually we divide the top and bottom, but it's a decimal, so let's, we would sort of like to multiply. Let's see, I could get 326 pi over 900, and then I could reduce that. So one way or another, I think you get down to reduce would be 163 pi over 450. Okay, so these first 4, 8 through 11, we're starting with degrees and asking us to convert to radians. Now notice I didn't write radians next to all of them, but none of my answers have a degrees symbol, so by default those are radians. Okay, let's keep going down the side, and then we'll come over to this 12. So pi over 2, Hopefully at some point you can just know that pi over 2 is equal to. But in the meantime, now I'm going to get pi. I know this is radians because there's no degree symbol, so I'm going to put my pi radians downstairs, 180 degrees upstairs. We could reduce these. This will be 90 degrees. But hopefully at some point, pi over 2, you'll just know that that is 90. All right, negative pi over 15. Again, we're going to multiply by pi on the bottom, 180 degrees upstairs. Those reduce, and this gives me negative 12 degrees. Again, don't forget your degree symbol, because without that degree symbol, that negative 12 would mean negative 12 radians, and we don't mean it to mean that. Okay. Let's see, we want to multiply again by pi and 180 on top, 180 degrees. And we can reduce these, and let's see, this would give us 135. The pi's, of course, cancel, right? That was the whole point of putting the pi downstairs. 135 over 2 degrees. All right, we want, or you could, put it as a decimal. That would work too. Okay. And the next one, negative 2. So that negative 2, it doesn't have any degree symbol, so that's radians. Now, normally, often, our radians are going to have a pi next to them. Because we know that half a circle, half a rotation is pi. So often our radians are going to be in terms of pi, but not always. So negative 2, this is negative 2 radians. So I'm still going to multiply by pi radians on the bottom, 180 degrees upstairs. So this one's going to be a little wacky. This one is negative 360 degrees over negative 360 over pi degrees. Right? Sometimes we'll write it like the fraction and then a degree symbol outside of it. All right. But this one is degrees. It just also happens to have a pi in it. Okay, so now let's look at this. It's sort of what we call the unit circle, but it's not necessarily a unit circle. So it's a xy coordinate plane. And then, so we've got these angles in standard position, and these rays out here are the terminal side. So we start here, we have 0 degrees and 0 radians. All right, the tall one is for the radians, the short one is for the degrees. So because we're going to have a lot of fractions in these, so that's why I'm leaving, put in this box, put in the radian measure, and in this one, put the degrees. Okay, so you're not asked, don't get out a protractor to measure these. We just know we have certain angles that we, are common angles that we were using last chapter. So this one is 30 degrees. If you want, we can just go around and do all the degrees first. So 30 degrees, this will be 45 degrees, this will be 60 degrees. Remember to include your degree symbol. Otherwise, by default, it's radians. So 90 degrees, 120 degrees, what is this? 135 degrees, 150 degrees, 180 degrees. So these are all the angles that have reference angles of 30, 45, or 60 as we go around. All right, so we have 180 degrees, we have 210 degrees, we have 225 degrees, 240 degrees, 270 degrees. All these should be sort of common to you. You should know what these are. This one is 300 degrees. This one is 315. This one is 330 degrees. All right, and now, so we know all those from last chapter, or we should be comfortable with those. Now, what are all of our common angles in radians? So 30 is pi over 6, because 30 degrees is 1/6 of 180. Let's go ahead and put pi in here. So 180 is pi. 30 degrees is 1/6 of that, so pi over 6. 45, there's 4 45s in 180, so this is pi over 4. It's 1/4 of pi, so pi over 4. We don't typically write this as 1/4 pi. Mathematically, those are the same things, but we say pi over 4. All right. How many 60s go into 180? That's a third, so this is a third of pi, or pi over 3. Pi over 2. All right, and now we think about 60 was pi over 3. Here's another pi over 3, so this is 2 pi over 3, 2/3 of pi. And then this is 1/4, 2/4, this is 3/4 of pi, so 3 pi over 4. And then this is 1/6, 2/6, 3/6, 4/6, 5/6. So 5 pi over 6. And so it helps if you're good with your fractions, right? So this is, let's continue with the 6th. So this is 6/6. This will be 7/6. So 7 pi over 6. All right. And then we also have a 6th over here, a 6th shy. We had this one up above. So this angle, if we went all the way around to here, to 330, that's 30 degrees shy. So that's, we saw already, was 11 pi over 6. So the pi over 6s are here, are here and here, right? So 5 pi over 6, 11 pi over 6. Pi over 6, 7 pi over 6. Now there are other pi's over 6s, but this is 2 pi over 6, which would reduce to pi over 3. So the pi's over 6s are sort of these shallow ones here and here. Then pi over 3s are going to be these more steep ones here and here. And then the 45s are the pi's over 4s. Okay. All right, so let's keep going. So we have 225. We saw that was 5 pi over 4. We saw that up above. Here we have 1/3 of pi, 2/3 of pi, 3/3 of pi. This is 4/3. So 4 pi over 3. This is a half a pi and another half a pi. So this is 3 pi over 2. That was 4 pi over 3. This will be 5 pi over 3. 7 pi over 4. We have 1/4, 2/4, 3/4, 1/4, 2/4, 3/4, 4/4, 5/4, 6/4 down here, and then 7/4. And then, of course, 8/4, which is 2 pi. All right. So again, we could always go back over to here and say this is 360 degrees or 2 pi. So depending on kind of the circumstances, we might call this 0, we might call it 2 pi. Okay, let's look at page 2, and we're going to start using on page 2, we're going to start looking at some formulas for, so the arc of a circle. Part of the reason that these radians, the radian measures were developed back in the 1700s and they started using them was because it made some formulas a little bit easier. So if you remember from geometry, if you wanted to find the arc length of a circle, we would say the circumference, 2 pi r, times the central angle times 360. So it was what fraction of the circle we're dealing with, right? So if this is 60 degrees, it would be 60 over 360, or 1/6 of the circle, right? So our central angle measure divided by 360 would give us what fraction of the circle we're talking about, and then 2 pi r was the circumference. Now, if that angle, theta, is in radians, then the formula reduces and becomes much nicer. And the formula is simply the angle theta in radians times r. So it certainly makes the formula a little bit easier to calculate. So let's look at an example. A circle with radius of 25.60 centimeters. We want to find the length of the arc intercepted by a central angle that measures 7 pi over 8. Let's see if I can focus that a little bit. 7 pi over 8. Okay, radians. So they give us, it's definitely in radians, so we can simply find the arc length, that's S, so we have S equals, and so we simply plug in 7 pi over 8 times the radius, 25.60. All right, and then what we do with that was, well, for this we would pick up our calculators and multiply those numbers together. We would put in a pi. We want to measure this one. Doesn't say what to measure it to, but let's say to the nearest hundredth, because they gave us it out to nice decimal places. We're sort of assuming that as far as significant figures, we're assuming that it's exactly that angle. So we'll multiply that together. We get 70.3716. We put in, 3.14, put in pi, use your calculator for that. And so I'm going to say that's approximately 70.37 centimeters is the length of the arc for that circle. Okay. All right, assume that Erie, Pennsylvania, and Columbia, South Carolina, are on the same longitudinal line. So that means north and south are right above each other on the globe. The latitude of Erie, Pennsylvania, is 42 degrees north. So that's how many degrees north of the equator that Erie, Pennsylvania is. And then Columbia, South Carolina, is 34 degrees north of the equator. So those are the central angles. If the radius of the Earth is 6,400 kilometers, find the distance between the two cities. Now, when we say distance, we mean, if you were on the Earth, not tunneling through the Earth, right? So the distance along the Earth, or the arc length, is really what they're looking for. So S is equal to theta R. Now the theta is this angle in here, and that angle in there is simply the difference in the central angles from the equator. So we're going to simply subtract those, and that would be 8 degrees. So the difference in theta would be 42 degrees minus 34 degrees, or 8 degrees. Now, of course, if we're using that theta, that's the theta we're interested in, we would want to convert that. So 8 degrees, 180 degrees, and then pi upstairs. So if we wanted to use our formulas, we would say that is 2 pi over 45 radians. So this is an exact measure for radians. Let's assume that. And so now we just plug it into our formula, right? If we're going to use this formula, remember the angle theta has to be in radians. And so we found what it was, and we converted it by multiplying by pi over 180 degrees. Okay, so that's 2 pi over 45 times 6,400. And so that's something like 893.609. And so probably just to the nearest, to the nearest whole kilometer, let's say. So to the nearest whole kilometer, that would be about 894 kilometers, about. So we're going to I'll use a squiggly equal sign to say about, meaning that I round it. And so about 894 kilometers. All right, next one is some gears. So 2 gears are arranged so that the smaller one, that should be a smaller one, I think. There should be an E in there. The smaller one drives the larger gear. So some motor, some shaft is going through here, and a motor is driving that. And so this movement is what's driving the bigger gear. All right, if the smaller gear rotates through 225 degrees, then through how many degrees does the bigger gear rotate? So let's just think about gears. And instead of angles, think about how far. Like, so for example, as I rotate this, we really want to almost just think of it as two circles that are touching and that they don't slip. The gears force, of course, these things not to slip. Like there's no slippage as the things rotate. So think of it as 2 circles, but the circles don't slip on each other, right? So the circumference of this, right? So they give us the radius. We can figure out the circumference, and they give us the radius for this one. Those are given down below. So whatever arc length, so they're touching right here, and so if this one rotates by so many, such a length, arc length, then this will pass through that same arc length. It's not going to pass through the same number of degrees because, think about it for a minute. If we had, let's exaggerate it, a really small gear and a really big gear, right? The small gear would have to rotate through several rotations to get this thing to circulate all the way around. So this one might go through 12 pi radian rotation, and this one may not have even rotated 1 full revolution. So they still will, the arc lengths will be the same, right? So as this thing rotates, the amount of arc length this one passes through will be the same as the arc length that this one passes through. Their rotation, the angle through which it rotates, will not be the same, but their arc length will be. Especially with gears, there's no slippage even possible with gears. All right, so we want to figure out what that arc length is. 225, again, let's do everything in radians because that's what our formula requires. So 225, well, we know that is what, 5 pi over 4 radians. So we can think about what arc length does the small one pass through. How much does it move along its arc? And that will be, of course, the same as the large one. So that's 5 pi over 4, and then times its radius of 3.13. And that gives us, I'm going to leave quite a few decimal points, 12.2914. All right, when we multiply this together. And then, so that's the arc length, and it's the arc length for the big too. So this was for the small circle. So now for the large circle, we know it passed through an arc length of 12.2914. And that's equal to theta for the large angle, the large gear, times its radius, 4.25. All right, and let's see, on my notes I round it, so let me get rid of that, and let's not round. So we want to do 12.2914, and we're going to divide that by the radius, 4.25, and I get my large theta to be, what did I get? I got 2.89. Let's just leave it as 2 decimal places for now. And then, but that's in degrees, right? You have to kind of keep your wits about you. Oh, sorry, that's not in degrees. That's in radians, right? That's radians. But they're asking through how many degrees does it go. So what we want to do is now convert that back to degrees. So it's radians, so we're going to do pi, if you want pi radians on the bottom, and 180 degrees upstairs. So when we multiply that together, we get to the nearest whole degree, we should get 166 degrees. Okay, so while the small one, it's smaller, so it's gonna pass through more degrees. It passes through 225 degrees, but this bigger gear is not passing through as many degrees. It's not rotating through as many degrees. The arc lengths will be the same, but the number of degrees rotated through will be less in the bigger gear. Okay, so that's arc length. Now let's also talk about the area of a particular, what we call a sector. So it's like a slice of pie, right, or a slice of pizza. We want to find out what the area is. And so we had a similar formula that we saw up above with arc length. It's the fraction of the circle that we're talking about. So the central angle measure divided by 360, that's the fraction of the circle that we're talking about, times the area of the circle, pi r squared. That formula is a little bit more simplified. If we use, again, theta in radians, it's 1/2 r squared theta. And again, that only works if the angle is in radians. So if we think about putting, we can kind of see how this formula would reduce. If theta was in radians, then the denominator wouldn't be 360. Instead, it would be 2 pi. So it would tell us what fraction of the circle it is. But then the pi's cancel. And so then we get 1/2. We get 1/2 theta r squared, or r squared theta, whichever order you want to put it in. Okay, so let's look at some examples of these. Find the area of a sector of a circle if the radius of the circle is 12 centimeters and the central angle measures 240 degrees. All right, so 240 degrees. Look back on the last page. We know what 240 degrees is. So 4 pi over 3. Why don't you pause the video and do example 4. All right, so I converted it already to radians. Again, we don't have to put radians without anything. We know it's by default radians. It's just sort of almost a placeholder for units. When necessary, we'll put them in, but we don't always need them. All right, so the area of that sector is 1/2. The r is 12 squared times 4 pi over 3. So you can leave this in terms, an exact answer in terms of pi if you want. This would be what? 1/2 of 144, 4 pi over 3. So we could reduce the 3 and the 144. We can reduce the 2 with the 144. It looks like we would end up with 96 pi, centimeters squared. So the area, just checking my math here, divided by 6. And then multiply by 4, 96 pi centimeters squared. Now, if you wanted to, like if you were trying to, I don't know, a pie-shaped room and you were going to carpet it, and you went to Home Depot and asked for carpeting, and they said, how much carpeting you want? You wouldn't say, oh, I need 96 pi cubic centimeters. You would say, oh, I need 302 cubic centimeters. Right? You would put it as a decimal, but often in mathematics we like to have exact answers, so that's perfectly acceptable as well. All right, next one, last problem. My rear window wiper rotates through 5 pi over 6 degrees, so that rotation is 5 pi over 6. Okay. The outer edge of the wiper, that's here, is 16.5 inches from the pivot point. So the pivot point being, that point right in there. All right, so 16.5, and then we have the inner edge is 3.4 centimeters away. what area is cleaned by the wiper. So what we really want to think about, I'm not drawing this perfectly to scale, but we want to think about the big area, and we're going to take away that little area, and then that's going to give us, I'm not drawing it perfectly to scale, but it's going to give us that. All right, so we want to take the big, like pretend like there's not this piece missing. Pretend like this is a big wedge. It's all shaded in. That's this one. Then we're going to calculate the area, just this little piece, and subtract those to get the area that the windshield wiper wipes from the window. All right, so let's do the large section, the large sector, if you will. And that is the area there is equal to 1/2 16.5 squared times 5 pi over 6. And I'm just going to do this with the calculator. 356.3744. And then the small sector, that area is 1/2 3.4 squared 5 pi over 6. And that's 15.13200. Okay. Don't really need that many zeros. I'm going to take off one since I use 4 decimal places here. 4 here makes sense. And then essentially the area wiped will just be the difference of those. And so the difference of those, let's say to the nearest whole inch, so that if we subtract these, right, that should give us, the difference should be something like, to the nearest whole inch, 341. I think the units were inches, right, inches squared. All right, approximately, if we're going to the nearest whole inch. Okay. So listed here is your homework. Remember that times 4 is the multiples of 4. Multiples of 4, multiples of 4, and then just do 114. Okay, and that is due next class.